I thought that before starting to implement the genetic algorithm, I will quickly try to explain what is it about and show a simple example. And at the end, that quick explanation turned out to be so long that it became a whole separate episode. So in this video, there won't be any coding, just me talking about the genetic algorithm. So genetic algorithm is a meta-heuristic, at least that's what Wikipedia says. The method goes through a few steps or phases inspired by Darwin's theory of natural selection, and it's commonly used for optimization and search problems. I'm going to break down those phases and illustrate them with an example. I prepared a few beautiful pictures. Here we go. So let's say there is a problem and there is an ideal solution of a problem, and we try to come up with various ideas that could serve as a possible solution for that problem. And instead of keep trying guessing the solution randomly over and over again, we keep track of which idea was a good one. Those can be applied later in some way, and the bad ideas, they will be very likely ignored in the future. And if we keep combining the good ideas, ideally we get closer and closer to the solution. That would be the general idea. The process always consists of these steps here, but since this algorithm is used in many different domains and needs to be adapted to those, I thought it's better if I'm also come up with an example to illustrate it and to make it easier to understand. Let's have the imaginary problem that there is a DNA molecule with 10 bases. I really wanted to have a genetic example to be relatable. And Google says that the DNA is built of bases, and the letters of the DNA bases are either A or T or G or C. So what we know in the beginning, that there is a 10 letters long sequence of A, T, G and C bases, but we don't know which letter belongs to which base. But for every guess, we can see how many letters of the sequence were guessed correctly. Now, instead of randomly guessing 10 letter long arrays over and over again, that could take a lot of time until all the 10 guesses are correct, we should find a quicker way to find out the DNA string. With that in mind, it's time for the starting step of the genetic algorithm, the so-called initialization, which means generating some strings with the length of 10 and randomly filling them with A, T, G or C. Here I generated a few. A collection of these strings is called population, and since I put here 8 strings, that makes the size of the population 8. The size of the population can be anything basically, but if the population size is too small, then the variety of the elements decreases, which could make it difficult to find the target. And if it's too large, then it can slow down the algorithm. In this case, 8 seem to be reasonable. After all the elements or candidates are ready, each of them needs to get a score, a fitness score. That fitness score is supposed to represent how close the candidates are to the ideal solution displayed above. So proper fitness function in general can help to find the target faster, and usually it's not an obvious task to come up with one, but in this case simply the number of the correct letters in the correct position will work fine as fitness function. So as for the first string, 0 0 0 0 0 0 1 0 0 0, the fitness value of this element will be 1. And same story for the others, this will be 1, this one 0, 1 2 5 2 5. So ideally, these two with the highest fitness values, they will have a better chance to pass their genes to the next generation. Let's see how to do that. It's time for the selection phase, the first step towards creating a new generation. The point of the selection phase is that the candidates with the higher fitness value will be selected with higher probability for the upcoming crossover phase, meaning that they can inherit their genes with more chance, while the poor guesses, they are likely to be forgotten. Just like all the other phases, the selection can be implemented in various ways as well. The one I would prefer in this case is the one that I think it's called Monte Carlo method, but I'm not completely sure about that. The point of it is that first the fitness values will be normalized, meaning each of them will be divided by the sum of the fitness functions, which would make the sum of these normalized values 1. And then if we get a random number between 0 and 1 and start to step up here, like is the random number smaller than the normalized fitness value of the first element? If yes, we pick the first element. If no, then we move up. Is the random number smaller than the sum of the first two elements' normalized fitness value? No, we move on. And let's say the random number was 0.5, so it's around here. And if we reach this point, is 0.5 smaller than the sum of the normalized fitness values so far? Yes, it is. And in the previous round it wasn't. So the cause of this change was the element number 6. Hence, this will be the output of the selection algorithm. And as this picture also illustrates beautifully, the probability of an element being picked is directly proportional to their fitness value. Moving on, the crossover is the next step. That's where a new element of the next generation is created. In this case, we choose two elements with the selection algorithm, the one I just explained, and mix their genes in a way. One common way for a crossover between two arrays is that the new element gets its first half from one parent, and the second half from another parent. That's perfectly fine. However, my personal preference is the one where each of the genes are randomly inherited either from parent 1 or from parent 2. Let's say elements 6 and 8 have been selected. Those happen to be the two fittest candidates, and their child will get each of its genes from one of the parents. And this new creature will be a member of the upcoming generation. After creating enough new members, which in this example is 8 since that's the size of the population, I need to go through them one more time and mutate them. That means that for every single element, every single base, there will be a small chance defined by the so-called mutation rate that its value is switched to something completely random. For example, a C can turn into a G even if none of the parents had a G in that position, or even if they didn't have a G at all. Because imagine if the 8 elements that were initialized in the first generation, none of those started with C. In that case, without mutation, there is no way that a DNA with a C as starting letter will be created since none of the parents have one. Mutation can solve problems like that. And too much mutation is quite counterproductive, like a 100% mutation rate, for example. That would mean that every single gene is randomly modified, in which case the whole genetic algorithm is pointless. So usually a 1% mutation rate is enough, and around more than 5% is usually not so helpful. Finally, after the selection and the crossover happened 8 times, resulting 8 new arrays, and mutation has been included, the children take over. The first generation is not needed anymore, they can be deleted, and their children will be the new members of the population. And it starts all over again for the second generation with the fitness function, selection, crossover, and mutation. And since the weak ones are likely to be ignored and the strong ones are likely to be selected for doing the crossover, the average fitness of the generations is supposed to get higher and higher, and sooner or later they will probably find an optimal solution. I mean, in this example it will surely happen, probably quite soon, to have a member with the fitness value of 10, but with the optimal population size, fitness function, crossover function, and mutation rate, this genetic algorithm can be helpful for much more complex tasks than this as well. I will implement this algorithm on the capsules in the next 2 videos. But spoiler alert, I'm about to tell how am I planning that. Remember, each smart caps object has a brain property, an array with 100 elements, where each element is a 4-bit long string, so they consist of 4 binary values 0 or 1. And there is also a make-move method in the smart caps class, which iterates through the brain array with the speed of 20 elements per second, so for 5 seconds altogether. And it imitates the key presses for the arrow keys based on the binary values. 1 means pressing a key, 0 means not pressing the key. Now imagine that instead of the 10 elements long DNA string, we try to optimize the 100 elements long brain array and find out what combination of key presses bring a capsule closer to a target point, which we can choose to be wherever, even outside of the canvas. The closer a capsule gets to the target, the higher the fitness value of its brain will be. The best ones will combine their brain cells, and the plan is that after a few generations, the capsules will be conditioned to reach the target. That's what I will try to implement in the next probably 2 videos. If you want to see how that goes, then see you soon.